Okay, here we go. Hope this video works. Here is the function defined as 5 sine squared x cosine squared x, which is what we're trying to evaluate the definite integral from 0 to pi over 2. It looks like the answer in Desmos is 0.9817, and it looks like this is the exact value, 5 pi over 16. Question is, how did I get from here to here using trigonometric identities? And if you look up in your calculus book how to do the indefinite integral of the sine of m of x times the cosine to the nth of x dx, they'll say something about if m and n are both even, you use half angle identities, and that's the case that we have here. And so here's the half angle identities. Sine of x over 2 equals the square root of. The key is that when you use a half angle identity, this angle is always twice this angle. So if you had a 4x here, this would be a 2x. If you had a 6x here, this would be a 3x. So we can rewrite identity 22 as the sine of x equals plus or minus the square root of 1 minus the cosine of 2x all over 2. If we square both sides, we get another form of identity 22. And similarly for the cosine squared of x, we get 1 plus the cosine of 2x over 2. So we're going to use this substitution, or these substitutions, in this problem right here, and that helps us get rid of these exponents. That's the key, is to get rid of those exponents. So if I go to board 2, I got a little careless over here, a little messy, but I'll try to talk through it. Here's the substitutions right here. If I multiply these two expressions together in the numerator, I get a difference of squares, 1 minus the cosine squared of 2x all over 2 times 2 is 4. And then I can break this apart into separate integrals. If you picture 1 divided by 4, that's where this comes from, minus cosine squared of 2x divided by 4, or minus 1/4. So I've still got the same expression. I just divided this 4 into both terms of the numerator. And then I'm going to take the definite integral of each of these terms. So I've got 5 times the definite integral from 0 to pi over 2 of 1/4 dx minus, and then I take this 5 times this constant minus 5/4 of the definite integral from 0 to pi over 2 of cosine squared dx. So this first term is going to be easy to evaluate. That's what I've done over here. The antiderivative of 1/4 is 1/4 x. And if you just work down this way, you'll see what this becomes. This minus 5/4 definite integral from 0 to pi over 2, I've got cosine squared. I'm going to use the half angle identity again and replace this cosine squared by 1 plus the cosine of 2x over 2. Then I'm going to picture dividing this 2 into this 1. That's where I get this 1/2 right here. So minus 5/4 times 1/2. 0 to pi over 2, this will just be an 1 dx, because I moved the out front, minus 5/4 of the definite integral from 0 to pi over 2 of the cosine of 2x. Oh, I forgot the 2 here. That's what I meant. I got a little careless here. So I moved that out front. And then you have to use U-Substitution. Okay, so I picture putting a 2 out here, so I actually have to put another 1/2 out. I'll let you be a little more careful than I was in doing this part. I think this actually becomes 5/16. But the key is the antiderivative of cosine is sine. I have to change the limits of integration, because when I use U-Substitution, I let U equal 2x. So when x is 0, u is still 0. When x is pi over 2, 2 times pi over 2 is pi. And the whole point is when I evaluate this from 0 to pi, I get a 0 here. So this is where we actually get our answer from. 5 pi over 8 is 10 pi over 16 minus 5 pi over 16 gives us 5 pi over 16. Okay, so I didn't talk all the way through this. You might want to pause the video and copy down some of the work and see if you can figure out what's going on. But that's the key, is using these half-angle identities when you want to get rid of a pair of even exponents involving sine to the nth times cosine to the nth. So there you go. Hope that helped.